You know, all the particles which are stuck inside the nucleus basically experience some kind of nuclear potential as a result of all its interactions. You know, inside the nucleus, all the nucleons, protons, neutrons, alpha particle will be under the effect of the attractive nuclear potential. Okay, we can say here, we can imagine the center of the heavy nucleus. We have here the nucleus. Inside we have protons, neutrons, alpha particle. These particles will be under the effect of the attractive nuclear potential, which has a negative value equals to minus V0. In general, it's about 35 minus 35 mega electron volt. If we have, for example, an alpha particle is coming out of the nucleus at any point here out, here we talk about the repulsive potential energy. It's a repulsive because we have a large distance, okay, between the center of the nucleus and the alpha particle. And this repulsive potential energy will be inversely proportional to R. You know, V in general in function of R equals to K Q of the daughter. When we have the particle is outside the nucleus, we talk about Q of the daughter times Q of alpha particle divided by R. Here we have alpha particle, and alpha particle is positively charged. We have the nucleus is positively charged. Between this one and this one, we have a repulsive force. And we can say we have uh, the domination of the repulsive Coulombic potential. Okay, this Coulombic potential equals to K Q of the daughter nucleus times Q of alpha particle divided by R. I will calculate it in the next slide. Okay, now we have the potential energy in terms of the distance. You know, the potential well, as definition, is the region of negative potential energy, okay, where we have uh, uh, we have all protons, or we have the nucleons will be on the bound states, okay, on the bound state. Inside the nucleus, we have protons and the neutrons on discrete energy levels. Okay. In general, as we have a negative potential energy, we cannot have a spontaneous emission of protons and neutrons. We need to use an external energy added to the system to have some protons escape, or to extract one proton or one neutron. So when we have a negative potential energy, so we have a barrier, and it's difficult or it's impossible to have a spontaneous emission of any particle from inside the nucleus. When we have a positive value, we talk about alpha particle in the next slide. When we have a positive value of potential energy, here we have to talk about the probability to have some emission of alpha particle. Okay, so now in the potential well, we have the distribution of protons and the neutrons on the bound states. And now we can talk about the formation of alpha particle. How does it happen? Two protons and two neutrons from the bound states will combine together to create or to form one alpha particle. But alpha particle will be in the quasi-bound state. Here we have the quasi-bound state, and alpha particle will have an energy between 4 and 9 million electron volt, mega electron volt. This is the energy of alpha particle created after the combination of two protons and two neutrons. Okay, so now I repeat before alpha particle comes out the nucleus, it experiences this kind of potential well, negative potential well inside the nucleus. When alpha particle comes out of the nucleus, we have the potential energy V. Let me calculate the value of V maximum. You know, here, in the case of when we have one heavy nucleus, and inside we have the alpha particle, the domination will be for the attractive potential energy. We have minus V0. Okay, it's here. When we have the alpha particle outside here, so here we have, for example, at this point, we have V maximum, V Coulomb maximum. Okay, so let me calculate this value. You know, the radius of this one will be R0. And when we have alpha particle outside the nucleus, here we have the total R will be equals to R0 plus R of alpha particle. Okay, here we have R0. Now I want to calculate the maximum value in the case, for example, I give you an example of Z equals to 72 and A equals to 200. Okay, we have a special, we have one heavy nucleus. I want to calculate the maximum potential energy of this kind of nucleus. In this case, you know, we have V in function of R in general equals to Q1, Q of the daughter nucleus times Q of alpha particle divided by 4 pi epsilon 0 R. Okay, you know, this one is a parent nucleus, and here we have the daughter after the escaping of alpha particle. We get daughter nucleus and alpha particle. Here we have alpha particle. Z or the number of protons inside the daughter nucleus will be Z minus 2, because the parent has Z. The parent has Z and A mass number. The daughter has Z minus 2 and A minus 4. And alpha particle has 4 and 2 protons and 4 mass number. Okay, so the total charge of D or alpha equals to the number, for example, for D, equal to the number of protons inside, which is equal to Z minus 2 times the charge of one proton, which is equal to E. Okay, and the total charge of alpha particle equal to the number of protons inside the alpha particle, which is equal to 2 times E. So we can calculate here R. I have the value of Q, D, Q alpha. We can calculate these values, and I have to calculate R. You know, R equals to R0, or in general, R equals to 1.2 femtometer times A power 1 over 3. You know this relation. You know, we can put the value of A, which is equal to 200 power 1 over 3, we get here 7.5 femtometer. This is, we can say, R0. This is the radius of the nucleus. Okay? To calculate the total R equals to 7.5 femtometer plus R alpha, it's about 1.5 femtometer. Okay? We can say here R alpha equals to 1.5 femtometer. We get here 9 femtometer. Okay, we calculated all the values here. We can find VR, which is equal to, we have Z minus 2 times E times 2E. We get 2Z minus 2 E square divided by 4 pi epsilon 0 R. You know the value of E squared divided by 4 pi epsilon 0 equals to 1.44 mega electron volt. Z equals to 72 minus 2, 70 times 2, 140. R equals to 9 mega and 9 femtometer. We get finally V at R0 equals to 25 mega electron volt. Okay, like this we can have an idea about the radius and about the Coulombic potential energy maximal, which is at the surface of the radius of the parent nucleus. Okay, now we can back okay, you know, we talked about two regions. First one, alpha particle is inside, and the second one, alpha particle is at the edge of the nucleus. Here we talk about minus V0, and here we have V maximal. Okay, we can say V Coulombic. Between them, when the alpha particle is going to come out the nucleus, we can say between them, we can talk for this region, it's called potential energy barrier. Okay, we can say it will be extended between R0 and R. So between this point, attractive potential energy, and the external medium, we have the potential energy barrier, where V maximum equals to Vc equals to 2Z E squared divided by 4 pi epsilon 0 R0. This one is the same, 2Z minus 2 E squared divided by, voila. It's approximated the same. Okay, we can eliminate 2 and we can write finally V Coulomb maximal equal to 2Z E squared divided by 4 pi epsilon 0 R0. Okay, so the potential barrier is extended from R0 to capital R. Okay, at this point, let me explain the last point here, very important. We calculated V, V Coulomb, V maximal equals to 25 million electron volt, which is equal to 2Z E squared divided by 4 pi epsilon 0 R0. Also, at this point, where at this point the particle is going to come out of the nucleus. Here we have V as a point R, okay, which is equal to 2ZE square divided by 4 pi epsilon 0 R. You know, this is the maximum value, and here you have the value where the particle is coming out. At this point, this value equals to equals to Q value, or equal to the kinetic energy of alpha particle. I will talk in the next slide how can we have alpha particle outside the barrier. Okay, now I assume that I consider that alpha particle is going like this. Okay, so at this point alpha particle is coming out, so it has a kinetic energy which is calculated before. It's approximately equals to Q, and at this point the kinetic energy equals to the potential energy 2z e squared divided by 4 pi epsilon 0 capital R. Okay, I give you an example. We have uranium 238, and you know, in this case we can calculate the maximum potential energy of this kind of heavy particle. Okay, in general, by calculation, we have a potential, a maximum potential energy equals to 35.6 mega electron volt. Let me write it. Okay, so as you know, classically, if alpha particle wants to come out of the nucleus, it must have at least 35.6 mega electron volt of energy to jump up of the maximum point of the potential barrier, and finally it can move away. But here we can ask, experimentally we found that the kinetic energy of alpha particle in this case, it's about 4 million electron volt. We have a particle of 4 million electron volt, and we have a barrier of 35.6 million electron volt. How this particle can come out classically and jump out of this barrier and moves away. Now we can ask, first of all, how can an alpha particle escape the nucleus if its kinetic energy is less than the potential barrier itself? Here we can tell uh, it's a quite puzzling phenomena. Classically, we cannot explain this uh, this kind of decay, alpha decay. So for this reason, we have to go to the quantum physics to explain this phenomena. Okay. According to classical theory, an alpha particle cannot escape from the nucleus. Classical theory fails to explain alpha decay. So we have another explanation to this phenomena in quantum physics, which is known as quantum tunneling, where, as you see here, the alpha particle can penetrate through the barrier potential energy via quantum tunneling. We can say tunneling effect. Okay, so it can go away out of the nucleus by using or by studying or under the effect of quantum tunneling. I want to explain this point. So, using quantum mechanics, George Gamow said that we have a finite probability for an alpha particle to penetrate the potential barrier and escape from the nucleus. So, Gamow's theory is regarded as a successful theory of alpha decay due to the following reasons. First of all, it's important to study Gamow's theory for the following reasons. First of all, we can have the expression of decay constant gamma, lambda. Lambda is called decay constant or decay rate or the probability of decay per unit time. We can find its value by using this theory. The second point, we can explain the phenomena of alpha disintegration. The third point, we can find a relation between the decay constant lambda and the energy of alpha particle, okay, between lambda and E. First of all, let me explain the quantum tunneling. In general, the particles in quantum mechanics has a wave behavior. What I mean, for each particle, for each motion, for each uh, particle, we can say it's accompanied by a wave mechanical equation. Okay, so the alpha particle inside the nucleus has a wave mechanical equation. Alpha particle in the potential barrier inside has a wave mechanical equation, and also alpha particle outside has also a wave mechanical equation. This equation can be calculated by using Schrödinger equation. Okay, so this wave mechanical equation associated with the particle. you know when Einstein wants to define the light, he said we have the definitions of light. We have photons, a quantized energy, photons, and we have a wave. So we have a relation between the quantity of photons and the length of the wave. Here we can say the same phenomena for each motion of particle. We can associate a wave function. It's called wave mechanical equation. So here the motion of particles can be understood by studying the wave mechanical behavior associated with the particles. If the motion of an alpha particle be treated as a wave mechanically, then we can say we have a finite probability that the particle can leak through the barrier potential V. Here, initially we have phi incident is the incident wave mechanical equation on the barrier, and here we have an attenuation of this wave, and it comes out with another wave function phi exit. Okay, so in quantum physics we can explain this phenomena. This wave function can be attenuated, or it can pass through the barrier, and we get another wave mechanical equation. So here let me divide the potential to three regions. First of all, inside the nucleus, we have region 1. Inside the barrier, we have region 2. And outside, region 3. Okay? And we have the wave incident comes here. Here we have refraction. and we get the wave function out of the nucleus. Let me simplify the calculation. First of all, I want to consider that uh, we have alpha particle here. We can say here we have zero potential. Here we have a maximum potential to this point, and here we have zero potential. Okay, you know, at this point, the particle is coming out, so I don't care about this region. Let me calculate the equations in function of this potential, rectangular potential. After this, we get some expression. We can apply it to our problem. Okay. Now, just to simplify the calculation, we consider that the potential barrier is rectangular in shape of width L and height V. You know, we have a height, let's say, equals to U here. So V equals to U between this point and this point. Here, V equals to 0 in the region 1, here in the region 2, and here V equals to 0 in the third region. Okay, and in the first one we have phi 1 wave function, in the region 2 we have phi 2, in the region 3 we have phi 3. Okay, as you see here, E is less than U. U is higher than E. Let me explain again the situation here. We consider that the potential barrier has a rectangular shape. We have to calculate, first of all, the transmitted probability, TP, and we can calculate the decay rate, lambda, which is the probability per unit time. And we apply this parameter to our case, where we have an exponential decreasing of the potential barrier, okay, of the Coulomb potential energy. Here, I want to show the motion of the wave in the first region, in the second, and the third. You know, Schrödinger equation gives us the solution of the wave function of each particle. First of all, you know the incident wave on the first wall of the barrier will be a part of this wave will be reflected back, and the second part will be transmitted. Okay, the transmitted part will be refracted inside the wall, inside the barrier. On the second wall, a part of this wave will be reflected back, and the second part will be transmitted. As definition of tunneling effect, so we can say the alpha particle will have a certain probability to tunnel through the barrier of height V. This is done by tunneling effect. Now I want to study the Schrödinger equation in the region 1, 2, and 3. First of all, let's start with region 1. You know, here in the region 1, we have V equals to 0. So we can eliminate V. We get here this equation. We can say 2me divided by h square equals to k1 square. So k1 equals to radical 2me divided by h square. As I said before, the solution of this equation must have two terms. One term uh, concerns the incident wave, and the second one will be for the reflected wave. Okay, the first one will be a equals a times exponential I k1r, and the second one will be b exponential minus I k1r. Okay, we go to the third region. You know, here, here we have only a transmitted wave. We don't have a reflected wave. So we have also V equals to O, and phi equals to phi 3. Okay, and so here we calculated, we said before, 2me divided by h square equals to k1 square. So here we get the solution with the transmitted wave, okay, equals to 3 c 3 exponential I k1 r. Now we go to the second region. You know, here we have one incident wave and one reflected wave, and V equals to a constant value equals to U. We can follow, we can calculate this one. We get this equation. The solution, we can say here, be careful, we have E minus U divided by H square. You know, U is higher than E. So this value is negative. We can put minus outside and we change U to U minus E. Okay. And we can say 2m U minus E divided by H square equals to K2 square. Okay. So we can say here K2 equals to radical 2m U minus E divided by H. Okay, the solution with two term of this wave, and the second one for the reflected wave. Okay, d exponential minus k2r plus e exponential k2r. You know, a, b, c, d, e are a constant. Maybe if we have time, we have to calculate them. So here, to resume, you know, as definition, the Schrödinger equation describes the form of the wave function that govern the motion of any particle, and also we can specify the behavior of any particle. We can say is the quantum physics representation of the particle. Here we have the region 1, and here we have the region 2 and the region 3.